Okay, welcome back everyone. In this video, I'm going to show a quick example of how to use Ampere's law to work with magnetic fields and forces. So this is actually number 68 from chapter 28. And so we have two very long wires which are carrying a current of I, and they're each a distance of A away from some imaginary center line. And there's a point P which we're interested in, and this is where we want to calculate the magnetic field due to the two wires. And we're given that this point P is a distance x away from the vertical line containing the two wires. Okay, so in part A of this problem, we're actually asked simply to draw the magnetic field. And so we remember that magnetic field lines wrap around a current source. And so we look first at the I, the current, which is coming out of the page at the top. And if our thumb represents the direction of the current, our fingers will curl in this counterclockwise direction, which means that at point P, the magnetic field would be going approximately this way. It would be tangent to a circle starting at the wire and going out to point P. So if this is I1, we could call this magnetic field B1. And if this is I2 going into the page, the thumb goes into the page and it would wrap clockwise. And so here there would be a circle which would go approximately like this, B2. And it's actually the same value of the magnetic field, because the magnetic field, due to a wire at a distance r away from it, the magnitude is simply mu naught I over 2 pi r. And in this case, we're talking about r being the distance along this dotted line, and hopefully we can see that that's equal to a hypotenuse, so it's a squared plus x squared to the 1/2 power. Okay, so that's kind of what happens with part A. There's the diagram. In part B, we are asked to calculate the total magnetic field at point P. And symmetry tells us that this is only going to be in the x direction, and then the y components will cancel out. But we still need some way of calculating the x and y components, and so we could say that if the magnetic field B has this value, and we can replace the r with a squared plus x squared to the 1/2, so if B is mu naught I over 2 pi a squared plus x squared to the 1/2, well then we're going to take that, and to get the x and y components, we're going to need to do sine and cosine. Okay, so if I'm careful about labeling my angle, and for example, if I label this my angle theta, so this is 90 minus theta, and likewise, you might find a more convenient way to do this, then hopefully you'll be able to look at this picture and realize that the magnetic field has to be at a right angle to these radii, and so that means that this is our angle theta right here, and so is this. So if we want the x component, bx, we're going to need the cosine of theta, and we can look at our diagram. So the cosine is actually going to be a over r, which is a squared plus x squared to the 1/2. And likewise, we can write that the sine of the angle is going to be x over a squared plus x squared to the 1/2. And so what this is going to do for us is, for example, if we want to write the magnetic field from the first wire in terms of its components, so bx1 I hat plus by1 j hat, well, this is going to be pretty straightforward. It's just going to be mu naught I over 2 pi a squared plus x squared to the 1/2, but then we need to multiply that by the cosine of theta, which is a over a squared plus x squared to the 1/2. So rather than writing all that mess, we'll just put it like this. How's that? And then for the y component, it's going to be mu naught I x over 2 pi a squared plus x squared j hat. So that is the magnetic field due to wire 1. Similarly, the field from wire 2 is going to have the identical x component, and the difference here is that the field in the y direction is going to be negative mu naught Ix over the same thing. So just like I promised, the y components are going to completely cancel out. And so the total field, so the field at point P, is going to be basically the two x components added together. So the 2 cancels out in the denominator. It's mu naught Ia over pi a squared plus x squared. Not to the 1/2, not anything like that, and it's just I hat. So this is our final answer to part B. Okay, now in part C, we want to graph this and take a look at it. And I'm only going to graph positive values, but you can kind of look at a bunch of different things. For example, we know when, so here's x and here's b, we know that when x is equal to 0, we're going to have b is equal to mu naught I over pi a. So take a look and make sure you can convince yourself of that fact. So let's make this right here be mu naught I over pi a. And then we know that when x is equal to a, we are going to have an expression that looks kind of like this. B is equal to mu naught I a over pi and then 2a squared. So when x is equal to a value of a, it's just going to be mu naught I over 2 pi a. So hopefully that's pretty clear. And you can plug in a bunch of other points if you want. The general trend is that we do have some sort of a turnaround or inflection, and it kind of looks like that. And we're not sure exactly where that happens. Okay. In part D, we want to essentially look at where the maximum is, and I think I can convince you that x equals 0 is a max. And I could do a derivative. I could do dB dx. I don't really need to do that though, because if you look at the expression for the magnetic field, any value of x that's non-zero is going to give you a smaller value. So the maximum value of the field is going to be when x is 0. And then finally, we want to find the magnitude of the magnetic field when x is much larger than a. And so for this, we need to go back to our equation for the field and plug in a couple things. But this time I'm going to write it a little bit differently. I can write this as a squared over x squared plus 1 times x squared. And what we can see by this expression is essentially it's going to go to 0. And you can work out the details of that on your own. But one thing that you have to consider is that when you're really far away from the two wires, so here's one wire and here's the other, and you're looking at a point P that's extremely far away, so that x is much larger than the distance between them. Well, if you look at this, the current enclosed by that loop is basically zero. So we're looking at a case where these two magnetic fields cancel each other out. And it turns out that there's applications where you actually run the current in opposite directions to make sure that the field cancels out. Coax cables are a good example of this. Okay, so that's it for this one. We'll see you next time.